First of all, here we're asked to sketch two curves on the same axes. I'd normally use a ruler, but I'm not going to bother. Here we have our x and y axes. You should know the shape of the graph y equals x cubed. It goes through the origin because when x is 0, y will also be 0. And in fact, it has a stationary point here at the origin. And it's supposed to go right through the origin. And then it goes up again. Okay, the line y equals 3 minus 2x, it's a straight line. The intercept, so comparing it with y equals mx plus c, in this case y equals minus 2x plus 3. The intercept is 3, so that's positive, so that's up here. The gradient, though, is negative, which means that you've got a straight line with a negative gradient. I will use the thing here, which goes down something like that. Gradient itself doesn't actually matter as long as it's negative. Now we can see here, so that's your 2 marks there. You don't need any more than that for 2 marks. You can see now that the curve and the straight line intersect at only one point, and that point is here. And because they only intersect at one point, it means that there is only one solution to the equation x cubed equals 3 minus 2x, because where these two, the curve and the straight line intersect, that's the equation that's being solved, and that's of course the same as x cubed plus 2x minus 3 is equal to 0. So this equation, which is actually this equation, has only one root because the curve and the straight line intersect only once. Okay, on to part B, which says show by differentiation that there are no stationary points on this curve. And I'm just checking that it's not actually the same curve. This curve, we're not x cubed plus 2x minus 3, you've got x cubed plus 3x minus 4. There's a similarity, but it's really nothing to do at the moment with part A. So to show by differentiation, let's start differentiating this. So we've got y equals, bring down the 3, reduce the power to 2, and then plus 3. Now, I'm a bit confused here about the stationary point thing, but I do know that for a stationary point, the gradient has to be 0. Sorry, I got to write dy by dx there. So dy by dx is equal to 3x squared plus 3. So I'm going to try and find the stationary points and see what happens. And I know that at stationary points, the gradient, or dy by dx, has to be 0. So let's put the gradient, that's 3x squared plus 3, equal to 0, and try to solve that equation. Now I can divide both sides by 3, which gives me x squared plus 1 is equal to 0, which means that x squared has to equal minus 1. Now you should know that you can't square something and get a negative number. It's impossible to find the square root of a negative number. So this equation has no solutions, which means that there cannot be any stationary points. There are no points on the curve where the gradient is equal to 0, because x squared, you can't solve the equation where x squared is equal to minus 1. Okay, and that's the explanation for part 2. This equation, so x cubed plus 3x minus 4 is equal to 0, it can only possibly have one root, because if we think about the shape of the curve, this curve, it cannot possibly be a cubic curve that does that. It must be a cubic curve that actually does something like that, which means there are no places on the curve where the gradient is equal to 0. Now, if you're solving x cubed plus 3x minus 4, so this is the curve y equals x cubed plus 3x minus 4, if you're solving the equation where x cubed plus 3x minus 4 equals 0, you are talking about the part of the curve where the line cuts, where the curve cuts the x-axis, or the line y equals 0. Okay, there must therefore only be one root. For example, if the curve looked like this, there would be 3 roots, but there can only possibly be one root if the cubic curve looks something like this, and it has to intersect with a horizontal line. There can only possibly be one root. Okay, let's think about what the factor theorem tells us. The factor theorem says that if you have an equation of the form f of x equals 0, if you can find f of some number, let's say f of 3, if you find that f of 3 is equal to 0, then it means that x minus 3 is a factor of f of x equals 0, which means that the root, or a solution is going to be x equals 3. Okay, so let's have a look at this equation here. X cubed plus x minus 10 is equal to 0. And there, f of x is equal to the left-hand side, which is x cubed plus x minus 10. Now, what I'm looking for here is a number that I can put in here instead of x, where I will end up on the right-hand side with 0. Now, it helps to think about the 10 here, because if you think about trying to factorize x cubed plus x minus 10, there will be 3 brackets if it factorizes completely. The 3 numbers, which you get here, here, and here, must multiply together to give you minus 10. So it's pointless trying numbers like 3 or 4, because 4 doesn't divide exactly into 10. I'm going to try 1, 2, 5, and 10, positive and negative, because I know that the numbers here, here, and here must be combinations of those. It could be that it goes 1, 1, 10, or it could be 5, 2, 1. The 3 numbers must multiply together to make 10. So let's start with f of 1. Well, f of 1 is going to be 1 cubed, well, that's 1 plus 1 minus 10. Clearly, that doesn't equal 0. If I try f of minus 1, well, that's going to be, all that happens is that this becomes minus 1, because minus 1 cubed is minus 1. This also becomes minus 1, and that clearly is also not 0, so forget 1. Okay, let's try f of 2. So f of 2 is going to be 2 cubed, well, that's 8, plus 2, take away 10. Aha, 8 plus 2 is 10, 10 take away 10 is equal to 0. Now that means that x minus 2 is a factor of x cubed plus x minus 10, which means that a root is going to be x equals 2, okay, which is an integer. So I've done the first part. Okay, let's have a go now at part 2. Now, I could use algebraic division here. I know that x cubed plus x minus 10 equals 0. I know so far that that can be written in this form, so that x minus 2 is this bracket here. And all I've now got to do is find the quadratic that goes here, so that that is exactly the same, so that this equation here is the same as this equation here. So what I'm looking for here is a quadratic which, when I remove the brackets from this lot, gives me x cubed plus x minus 10. Now, for a start, I know that this has got to be x squared. That's fine. They give me that anyway. The number that goes on the right here is going to have to be plus 5. And the reason for that is that to get minus 10 here, I'm going to have to do minus 2 times this number, which has got to be, therefore, 5. Now, I'm just looking then for the x term. And here's the clever bit. I could do like I say, I could do algebraic division, where I see I'm going to divide x minus 2 into x cubed plus 0x squared plus x minus 10. But actually, that's going to take me a while. I'm not going to bother with that. All I need to actually do is figure out what number goes here. Now, if I look at my terms here, I notice that there are no x squared terms. So the coefficient, or the number of x squareds, must be 0. Well, let's just have a look at where the x squared terms come from. If I do minus 2 times x squared here, that gives me minus 2x squared. The other x squared term must come from doing this one times this one. So if I've got minus 2x squared there, I must get plus 2x squared here. So this here must be plus 2. And what that means then is that what they call A, so it means that A will have to be 2, just by comparison. A is 2. P is what they call the number here, so P is also going to be 2. And Q, which is this number here, is equal to 5. Okay, now, by considering the quadratic equation found in part 2, well, that's the quadratic equation. Okay, so I found that x squared plus 2x plus 5. So remember, my whole thing was x minus 2 here. Okay, and that equals 0. So I've already established that one of my roots to my solution, to my equation, is x equals 2. Let's now have a look at this quadratic equation. So we've got x squared plus 2x plus 5 is equal to 0. Now I'm going to try solving that, and I know that I can use the quadratic formula where a is 1 and b is 2 and c is equal to 5. And if I start solving that, well, x is equal to um, minus b, so that's minus 2, plus or minus the square root of b squared, well, that's 4, so it's 2 squared, minus 4 times 1 times 5. Now, there's no need to go any further. I can see, if you look at the square root here, it becomes the square root of 4 minus 20, which is the square root of minus 16. And you should know that we can't find the square root of a negative number. Therefore, this solution, this part inside the square root sign, by the way, is called the discriminant. And if the discriminant is negative, it means that the equation, the quadratic, has no solutions. So in this case, this equation has no solutions, which means that x equals 2 is the only root to the cubic equation that we've been given. Okay, so the cubic equation only has one root because the square root of minus 16 can't be found. Right, the last bit's only worth 1 mark. It's worth looking at the 3 equations in parts A, B, and C. This is the one for A, this is the one for B, this is the one for C. And in each case, using 3 different methods, we actually worked out that each of these equations has only one real root. Now, if we look at the general form of what they're asking us here, if you've got x cubed plus rx minus s, where r and s are positive, okay, and you've got a minus sign here, which makes all of these negative, you will be talking about equations, cubic equations, which are of this form. Now, in all 3 cases above, we found that there was only one real root. I can't do any more investigation for 1 mark, but I would say this suggests that this general equation, any equation of that form, there will be only one real root. I can't check that, but it's a good stab, and we're only suggesting here, and that is in fact the correct answer.